So we can create technologies that instead of using fossil fuel energy to provide cooling, we can create technologies that harvest energy that's already out there and use that to provide cooling. That can make a big dent in our fossil fuel consumption, right? It can really help to mitigate climate change. And so that's really the end goal here, is to harvest energy instead of generate energy that comes from non-renewable sources.
Welcome to Growing Impact, a podcast by the Institute of Energy and the Environment at Penn State. Each month, Growing Impact explores the projects of Penn State researchers who are solving some of the world's most challenging energy and environmental issues. Each project has been funded by the Institute's Seed Grant program that grows new research ideas into impactful energy and environmental solutions. I'm your host, Kevin Slyman. Cooling is an energy-intensive process. Whether it's your home or the food in your refrigerator, that cooling takes a lot of energy. In fact, air conditioning accounts for about 19% of electricity consumption in U.S. homes. In commercial buildings, air conditioning accounts for about 14%. But the energy needed to circulate that air consumes an additional 18%. In addition to energy consumption, cooling also emits greenhouse gases, which are impacting the climate, which requires more cooling. It's a vicious cycle. But what if there was a way to harness existing energy to cool? A research team at Penn State is exploring materials that cool their environment when they're strained. This technology could provide a sustainable way to cool everything from a building to a laptop. Welcome to Growing Impact. I really appreciate you taking time coming on the show and talking about your research. Would everyone go around and can you introduce yourselves?
My name is Wenjie Li, currently an associate research professor at Department of Material Science and Engineering at Penn State University. My research focus is mainly on developing functional and structural materials and devices for sustainable and environmentally friendly energy applications, such as the elastocaloric cooling technology that we are going to talk about today, as well as thermoelectric power generation and cooling and hydrogen storage materials.
My name is Herschel Pangborn. I'm an assistant professor of mechanical engineering here at Penn State. Also have a courtesy appointment in the aerospace engineering department. My research broadly is at the intersection of energy systems and autonomy. So we look at how do you model the energy dynamics in a range of different systems, ranging from hybrid electric aircraft to robots to microgrids. And then once we understand what the behavior of those systems is, then we try to exploit that knowledge to make them more efficient, higher performing, safer. And that really involves using the theory of autonomy and decision making to make those systems operate themselves better.
My name is Na Liu. I'm currently a postdoc research fellow in material science and engineering in Penn State University. And so my background was about scanning probe force microscopy, characterizing the functional materials. Since I joined Penn State team, my background changed to use the phase change materials such as chip memory alloy or vanadium oxide, those kind of oxide material to do some thermal management objectives. Generally speaking, just convert the waste energy to useful energy.
My name is Kaylee Hayes. I'm an undergraduate student researcher in the Department of Mechanical Engineering. And my research is primarily on simulation and modeling of dynamic systems. So in the past, I've done research modeling vehicle dynamics of some autonomous robots. And currently, I've ventured into thermal simulations a bit with this project.
We should also acknowledge Andrew Thompson, who's a PhD student in my lab and has been working closely with Kaylee throughout the last year or so. Andrew's had a really exciting internship this summer. So he's not joining us here, but he has been very involved in the project and has been a great mentor as a graduate student.
You're working on a facet of elastocaloric cooling. Can you explain first, what is elastocaloric cooling? And then could you share about how it works?
What is the elastocaloric cooling? It's kind of a new technique. So we want to use it to replace the traditional refrigerator cooling because it has a lot of advantage. So what is that? The concept is that is a technology that uses the property of certain materials. We are talking about chip memory alloy in this project, which is a phase change material. So we want to use this kind of certain material to create a cooling effect through some kind of external mechanical stresses. such as bending, compression, or tension, or stretching. All those kind of forces can somehow apply the force, and then the material can generate the delta T in order to cool the surrounding atmosphere.
So this material, when manipulated, compressed in some way, some kind of force is put on it, it actually creates a cooling effect. It cools off instead of warms up.
It warm first and then cool down. So this is chip memory material. We are using so-called chip memory alloy, which is the metal, for our elastomeric application. So I want to just introduce this material a little bit. They are not new. So all the kind of application are due to these two important effects. First is chip memory effect. So chip memory effect is this material, you can easily bend it. For instance, at room temperature, you bend the material and the material just deform like significantly. And this deformation will not go back to its original state. But you can apply the heat and then this material just go back to the initial shape. So this is called chip memory effect. Another very important effect is called superelastic effect, which is used for this elastomeric cooling technology. So that effect is, so at room temperature, for instance, that's all because this transformation temperature below the room temperature. And the chip memory effect is the transformation temperature above the room temperature. So it's how these two are different from each other. So for the chip memory for the superelastic effect, when the transformation temperature below the room temperature, so you are bending the material and it can be deformed significantly, but when you release the force, without additional heating, it can go back to the initial shape. So we are using this material for our application.
One way to think about this is, fundamentally, all cooling technologies for things like HVAC, it's about trying to move heat in the opposite direction from where it wants to go, right? Heat wants to make the cold things hotter, right? But when you're trying to cool something, you're trying to make something that's already cooler even colder than its environment. So you're trying to pump heat against its gradient. So traditional systems like a refrigeration cycle, right? You use a big compressor and fans that consume a lot of electrical energy. And you use that to change the phase of a refrigerant, and you use that to pump the heat across its gradient. What we're trying to do is take mechanical energy, right? That, vibration or compression, and use that through this material to create that gradient that can drive heat in the direction you need it to go for cooling.
The purpose of this project is trying to utilize this materials, device, and technology for the future smart building applications, which requires ideally even a small mechanical pressure is applied on the materials. It should be able to trigger this elastomeric cooling effect. But one of the challenges right now is a lot of materials, it requires a certain amount of pressure to trigger out this elastomeric cooling. So for the material science, one challenge is how we can lower the threat of this applied force to trigger this cooling effect. So yeah, generally speaking, it can be used in the various applications, not only the smart buildings, but primarily for this specific project, we are targeting all the smart buildings.
I would think about any context in which you have some kind of mechanical force that is right now not being used to harvest energy. So that could mean people walking on a floor where, right now their footsteps just go into the ground and don't go anywhere. But could you use that energy to actually provide cooling, right? Or you could think about a compressor in a refrigerator or a fan, right? Something that already they have mechanical dampening. They have springs under that compressor that's designed to take its really, strong vibrations and dampen those out so it's not shaking the whole building. Instead of just trying to dissipate that energy, again, where it doesn't go anywhere, can you harvest it and use it for cooling? You could use this in vehicles like aircraft that undergo, mechanical stresses as they fly, where you could try to use that to provide cooling to the components in the aircraft, where you have all kinds of batteries, electronics, and other things that need that cooling. So there's a lot of places where you could potentially harvest energy where right now it's not being used, and this would be able to utilize that to provide some benefit.
Yeah, maybe another very simple example that we just had a very brief discussion with Na earlier today about the lab, for example, the laptop.
So imagine you have this material which is inserted in your computer, and then you are typing your keyboard while you are using the computer. So that is kind of mechanical force you are applying like in your daily life quite often. Imagine you can using that kind of force and to cool your computer.
So this already sounds like this has multiple potential places where this could actually show up, from a keyboard to an airplane to the floor of a building.
Yeah, from small scale to the large scale.
Why is elasticaloric cooling a technology that deserves more attention and investment? And is there data or background on this that talks about the technology or shows how the technology is superior to maybe other cooling technologies? Or if it is, I guess, maybe that's a discussion point. Like, is it actually superior to other cooling technologies? And if so, how?
So I say generally speaking, the reason why the elastic cooling deserves a more attention and investment is that it can simply provide an efficient and environmentally friendly alternative to the traditional cooling systems, such as vapor compression technique. So first of all, it has a positive environmental impact. So traditional cooling system you often use refrigerants that inevitably generates greenhouse emissions, leading to the climate change, which is harmful to the environment. Where this elastic cooling technique can just potentially eliminate the needs for those harmful chemicals. Secondly, this technology can be more energy efficient compared to the conventional cooling methods, and also relatively it represents a novel approach to the cooling and utilize the existing mechanical force, which is everywhere around our life. There's some preliminary research has shown that this technology can convert the mechanical work directly into the cooling with minimum energy loss, and that's reduce the energy cost for the cooling application. And according to the very recent report from Department of Energy, this elastocaloric effect shows the greatest energy saving potential among the various caloric cooling, and also compared to the conventional cooling technologies that can reach more than 40% of energy consumption saving over the conventional way. Maybe the last but not least is in terms of the performance and the scalability. So it provides rapid cooling cycles because we are targeting to use alloys, which has a high thermal conductivity. So it can benefit the very precise temperature control. So that can further extend the application of this technique to even, for example, the wearable devices to monitor your body's conditions and also make the people feel cooling and comfortable during the hot summer. What we want to do is to develop the new materials and design systems for the scalable and practical device in the future.
So one thing I would say in terms of the broader impact here, something around 30% of our energy consumption in the US goes to buildings. And somewhere around 40% of the energy used in buildings is for heating, ventilation, and cooling. Right. So it's a huge chunk of the total energy that we produce goes into heating and cooling. So most of that energy is coming from non-renewable sources. It's coming from fossil fuels. So we can create technologies that instead of using fossil fuel energy to provide cooling, we can create technologies that harvest energy that's already out there and use that to provide cooling. That can make a big dent in our fossil fuel consumption, right? It can really help to mitigate climate change. And so that's really the end goal here, is to harvest energy instead of generate energy that comes from non-renewable sources.
So this use elasticaloric cooling, we can incorporate this technique with some other like technology. For instance, the 3D metal printing and also the AI. This kind of technology can be included and incorporated in order we can print any kind of sizes or shape about the devices, and which are potentially used in any kind of scenario.
Can we talk about your project and its objectives and what you're hoping that will, what you hope to do at the end of the Sea Grant as it comes to a close here, and then maybe even moving forward, what that could potentially looks like?
We are trying to develop the chip memory alloys and a related device to address the challenges from both manufacturing and the simulation studies. So first of all, we have developed different chip memory compounds with a large latent heat, low mechanical hysteresis, good thermal conductivity, and high recoverable strain. So all these compounds can cover a broad temperature span that can be utilized for the different applications with a specific temperature requirement. And secondly, we have developed a miniature device using the chip memory alloy tubes, showing that we can demonstrate quick temperature response and the large temperature difference capability. And also we have done some preliminary 3D printing of the chip memory alloys, and we just found out that it can provide, it shows a large latent heat of the materials. Since I have talked about this latent heat concept a couple of times, so I want to briefly bring the idea what exactly it is. So the latent heat indicates the amount of the heat required to change the state of substance without changing the temperature, which means specifically for the elastocaloric materials, the larger latent heat your materials have, the more heat you can absorb from the surroundings before it goes to the phase change and deform, and then we transfer this heat to other places in order to make our surrounding cooler.
Ultimately, 3D printing, what it allows you to do, one of the things it allows you to do is fabricate parts that would be very hard to build by any other means, right? Other manufacturing processes. And so where that ties into some of the modeling we've done is that through the models Kaylee's created, we can predict things like what would the efficiency of the device be with different thicknesses and different lengths and different diameters. And if that optimization tells you a particular diameter might be best, we'd either have to find a way to manufacture that component or go out and buy it on the market somewhere. And that can be hard to do, right? Suppliers of these materials, right? It may not be exactly the right chemistry. It may not be exactly the right form factor. What we can do with additive manufacturing is we can print exactly the ideal part that our models tell us is going to make the best device out there. So that's where we've been able to use this modeling to inform what we manufacture and then use 3D printing to actually manufacture it and test it out.
Kaylee, can you talk a little bit about the modeling part of it?
Yeah, sure. So basically, the way that we're modeling this is we're using some basic assumptions and knowledge about how heat transfer works, some knowledge about how stresses in materials work, and knowledge about the specific SMA materials to create an equation-based model that lets us simulate how a hypothetical device or even an individual piece of the material would behave under certain conditions. So you can pick room conditions, room size, ambient temperature, basically environmental factors, and you can adjust that. So you can say, okay, we have this kind of device that we'd like to look at. How would it perform under these conditions? And then in slightly different conditions, what are your trade-offs? And we can also use it to do some design parameter adjustment as well. So for example, okay, at what point is the thickness of this device too much where the benefits tend to be outweighed by, some other effects that you might not have predicted? So the model is really valuable in that it helps us hone in on these parameters more precisely than just guessing or doing calculations, especially because you can save a lot of calculation time. So rather than doing these things by hand or estimating or guess and check, you can sweep over a range for a parameter and say, okay, this is the value we're looking for, so this is the value we're going to choose. So that's basically the point of the simulation, is that it lets us pick design parameters more precisely for this device than we might have been able to without it.
We have the folks you're hearing from here are really, world-leading experts on the material science. And at Penn State, we have facilities and test beds that allow us to characterize materials, using the latest and greatest methods that are out there. And so, these experts are able to tune in exactly, what's the best alloy, what are the best materials, do the testing to characterize their properties. And then in that same week, we're able to take that test data and plug it into the models that Kaylee's developing and understand what are the device level and the system level impacts of those improvements in material properties. And that ability to translate from the fundamental material science into the system level understanding and the dynamic understanding, I think that is really unique about this project and how multidisciplinary it is. And it's also a unique thing about Penn State, the fact that we have this range of expertise and we have mechanisms like these seed grants that can give us the opportunity to collaborate in that way.
What kind of groups and or, whether it's organizations or people that could potentially benefit from this knowledge and application?
Just can simply benefit a wide range of like industries and stakeholders as well as the general public, just by offering the improvement in efficiency, sustainability, performance. So I'll just maybe give you a couple examples. Like for the HVAC, the heating, ventilation, and air conditioning manufacturers and consumers for more efficient, environmentally friendly products, or just bring you the reduced energy bills for your house. And also, like Herschel just mentioned earlier, like in electric and maybe the hybrid vehicles, this technology can be used for like efficient battery thermal management and also the climate control systems. Also, like in the electronics and IT industries, it's just meant now bring about this topic that it can be improved cooling solutions for the data centers and consumer electronics, preventing the overheating and extending the lifespan of the device. Also, as we just bring out this topic earlier, that it can beneficial the portable medical cooling devices for the medication, which requires very precise temperature control and improving the patient comfort and care qualities. Also, for the larger scale, it can enhance energy efficiency and reduce the environmental impact of the refrigeration and like in the units like the supermarkets or food processing and storage facilities and so on. And also we covered a little bit, I would say, for the more like frontiers of the advanced science, this technology can benefit the stakeholders for like the renewable energy sectors, such as a solar power system by managing the heat more efficient, and also for the geothermal systems through the efficient heat exchange mechanisms. Also, like in the aerospace or defense area, it is interesting for people who want to utilize this technology in the aircraft for the more efficient and lightweight climate change system to ensure the proper functioning of the onboard electronic systems and equipment by like thermal management during the whole like long-term space explorations.
Another thing we do, and I think this is why a lot of us choose to be in academia, is we train students, right, to be the next generation of leaders in the space. Part of what we've had the opportunity to do through this project is to work with Kaylee and Andrew Thompson, who I mentioned as a PhD student, and train them in how to do this multidisciplinary research. And for me, that is a huge part of the value of what we do. My hope is that they will take what they've learned through this project and go on to do way cooler and greater and better things than anything we do in our careers. And I think they're set up to do that.
So it's been interesting to see how a research project like this can really develop over a longer time scale, like a year as opposed to 2 months. And it's also given me a lot of opportunities to improve some like technical writing skills that I didn't really have before, and a lot of communication stuff too that you don't really get from anywhere except just doing it. So I presented a poster about my work on the simulation for this project. And that's a really cool opportunity to get used to putting my work out there that I wouldn't have otherwise if I wasn't on this project.
You have 20 seconds with a industry leader, some world leader, whatever it is. You have 20 seconds to talk about your project. What do you tell them about this project and why it's important?
The Elasto Caloric project is a pioneering and innovative and environmental friendly and energy-saving cooling technology to achieve efficient cooling by cyclically pressing and releasing the shape memory materials. So this technology is providing solution for sustainable development with potential benefits for the environmental economy, workforce development, and promoting the energy security and independence.
There are a double-digit percentage of our energy goes into heating and cooling in buildings. That is emissions, that's cost. And so rather than take energy off the grid in order to provide this cooling, let's try to take energy that's already out there that's not being used, right? In the same way that we use solar panels, that we use wind turbines, right, to obtain renewable energy. This is a way of extracting mechanical energy from motion, right, and turning that into cooling in buildings as a new way of providing. Almost think of it as free energy in a sense, energy that's there that we're just making use of in a new way.
Thank you so much for being on Growing Impact. I really appreciate it. Na, Kaylee, Wenzi, Herschel, thank you so much. It was great talking with you about this, and I learned a lot because this is something that's amazingly complex, and I really appreciate you guys working on it. So thank you for being on here and talking about it.
Thank you for coordination.
Yeah, appreciate it. Thanks for the
Yeah,
opportunity.
thank you.
Thank you.
On this one.
This has been Season 5, Episode 9 of Growing Impact. Thanks again to Wenji Lee, Herschel Pangborn, Na Lu, and Kaylee Hayes for speaking with me about their project. To watch a video version of this episode and to learn more about the research team, visit iee.psu.edu/podcast. Once you're there, you'll find previous episodes, transcripts, related graphics, and so much more. Our creative director is Chris Komletic, with graphic design and video production by Brenna Buck, marketing and social media by Torian DeViro, and web support by John Stabinger. Join us again next month as we continue our exploration of Penn State research and its growing impact. Thanks for listening.